and networks and so on. Anyway, coming back to CNNs, as you can see, the C over here stands for convolution. Some of you are in the computer vision class where I've already covered this, but majority of you are not. So even though it may be boring for some of you who already have seen it, but for the benefit of, because more than half the class have not seen that part, I really wish everybody who was taking this course was also taking the computer vision. This way your background will be very, very nice. But anyway, let me go for 5 minutes, then I'll take a break, and then we'll go into the details of CNNs. Okay, so convolution is a fundamentally very, very important concept. Okay, those of you who are electrical engineering majors know it inside out. Because in electrical engineering, you go through signals and systems or signal processing where the whole concept is based on convolution. But anyway, the fundamental idea is like this. All linear systems in nature support convolution in the sense that if we give it, so let's pretend this is a time system which produces an output as a function of time, then according to the law of convolution, the output over here is related to the input by, so this is our convolution symbol, by doing the convolution with something called h of t, which we call the impulse response. Okay, what is an impulse? Impulse function delta t is basically, it looks like this. It has infinite amplitude, zero width, such that if we integrated dt, the answer will be 1. Okay, so if we take the same system, feed in delta of t, whatever output we give, so if we feed in this, whatever output we get, we call this h of t, and that's why we call it the impulse response. Okay, once we have the impulse response, then as I mentioned, any input can be convolved with the impulse response to determine the output. So then it becomes extremely easy. Okay? In terms of actual computation, here I said this is convolution with this. What is convolution? Convolution in the continuous domain is an integral with x of t minus tau, h of tau, d tau, or also could be written as x of tau, h of t minus tau, d tau. Okay, so what exactly this tau business over here? Let me try to explain it in very, very simple terms through a simple example. Okay, let's say you have a signal like this. Sorry, 0, 1, 2, 1. Let's pretend this is x of t. Okay. Let's pretend this is h of t. Okay, this is 1. Okay, so first let's try to see it without going into the actual calculations. What is convolution doing, right? Okay, so let's focus on this part, x of t minus tau. Okay, over here, if this is the t scale, first let's change it to a tau scale. So in the tau scale, all we have done is change t to a tau, so it will still be 0, 1, 2. Nothing will change. Okay, now let's make it, so this is x of tau now. Okay, now let's make it x of minus tau. Because as you can see, there's a minus involved over here. So what will minus tau do? It will basically flip it on the time axis. So this will become -1, -2. So this is how the x of minus tau will look like, right? Then what about x of t minus tau? Okay, so this is basically a shift by t. Okay, so then this will look as this will be t, this will be t minus 1, this will be t minus 2, and this will be x of t minus tau. Right? Okay, so now if you take a look at the convolution integral, so essentially what does this mean? That means start varying t, which basically means, and before we start varying t, we flip it. So we flip this, right? And then start changing t, so that means start sliding it. So as you will see, as we start sliding it, this will go over here, then further keep sliding it, maybe will come over here. Once it comes over here, you can see we're multiplying it with h of t, then integrating it, which is simply area in the curve. So basically, as you can see, whatever the overlap is, if we accumulated it, that will be the answer of the convolution. Okay, so we can go through and write down the equations, exact equations over here, but and we did that, I think, in the computer vision course. So for you guys, as long as we understand the fundamental idea, that's good enough. Okay, so basically what it will do is, as you will see, is up to, okay, once, so let me draw, so this was 4, 5, 6. Okay, here's the flipped version of it, which we are sliding. Okay, so this is at t equal to 4. So you can see the multiplication of this will produce a 0 answer until t equal to 4. Once we increase it, this is slightly greater than t equal to 4, then you'll see it will start to accumulate some area, right? For example, what will happen when t is 5? So let me draw the picture when t is 5. When t is 5, won't it look like this? What will be the value of the integral then? 0.5. It's like, half of a square, right? So as you can see, starting at, so this is the convolution, x of t convolution with h of t. So starting at 4, it starts to increase. Then at 5, it is 0.5. You guys agree? So at 5, let me pretend this is 5. So exactly at 5, we know the value becomes 0.5, and it's gradually increasing. Okay, now let's make it 6. What will happen at 6?
Maximum.
So now you'll see it has the maximum overlap over here. Okay, and what will be the area?
1.
See, this half is 0.5, this half is another 0.5. So it will be 1. So basically, what it will do is, at 6, it will reach the maximum, which is 1. Now if we keep sliding it further,
Decrease.
so we'll start to decrease. For example, let's say it's here, or even before. So see, this is the area that's common. And so basically, the answer of the convolution will be something like this. 7, at 8 it will go back to 0. Right? Because if you put t equal to 8, what will be, so t equal to 8 is over here, there's no overlap. Okay, so in short, convolution produces the maximum value when there's an overlap between the two signals. Okay, so we flip, we slide, multiply, and integrate. So that's what the convolution does, right? Okay, how does this relate to neural networks? Let's take a break. After the break, I'll show you how it does, and then we'll go from there.